The next component of the cell I would like to have a look at is the cathode, which is shown in blue here. And the requirements for the cathode are a good electronic conductivity, and ideally we want to have a mixed conductivity. So why is that? First of all, we want electronic conductivity because we facilitate the reduction reaction on the cathode, and we want to efficiently transport the electrons to our reactant here. So this is why we need good electronic conductivity. Of course, you know that often an ion will be needed at the cathode as well as a reactant, and this is why a mixed conductivity would be most advantageous. So certain electronic but also ionic conductivity. The cathode, just vice versa to what we said for the electrolyte, also has to be compatible with the electrolyte. This is especially relevant when we are talking about chemical or thermal expansion of the material. So when the electrolyte changes its volume or the cathode changes its volume, they should be able to compensate for these changes relative to one another. Likewise, we would like to have a high activity in oxygen reduction because that's the typical reaction we are facilitating. We need a chemical stability in oxidizing atmosphere. So typically we would like to have no metals in here. And we want a thermally stable material at varying temperatures and an open porosity for high surface areas. So this open porosity in high surface areas is typically to just offer more sites at the surface to react, and therefore we would have less activation losses. So typical materials for the solid oxide fuel cell are mixed conducting perovskites, like for example strontium or calcium doped lanthanum manganese oxide or lanthanum cobalt oxide. The cathode material itself can undergo a variety of degradation mechanisms, and here is a selection of them, and this should also show you why, on the one hand, the cathode material has to be carefully selected itself and be active for itself, but why it's also vital to have compatibility with the adjacent phase, and that will be the electrolyte, of course. So what might happen are, for example, crystal defects and metastability. So crystal defects, of course, meaning that you kind of have building errors in your material, which might hamper your activity. And metastability also refers to that. So if something is stable, it cannot be altered in its state easily. If something is metastable, it means it is unstable relative to another state under certain conditions. Another degradation mechanism is so-called microstructural coarsening, and this refers to particles kind of merging into one another. And you can readily see here that the most significant effect of this is a shrinkage of surface area. Therefore, you lose active sites and therefore you lose activity in your corresponding reaction. Also, surface chemistry alterations might happen. So, for example, if you introduce dopants in your material, and as we've seen, that's pretty typical, it might migrate to the surface out of there and do effectively a phase segregation and a loss of activity of the main bulk material might be the result of that. Another factor is a reaction between adjacent phases. So if your cathode relative to your electrolyte is not 100% stable, you might form some kind of merging products in between. So this pretty much depends on the material, but ions might migrate in one or another phase and therefore hamper your activity. Also, delamination is an important factor, especially if you think about shrinkage and expansion of a material. So delamination hereby referring to a loss of contact due to, for example, a shrinkage, as it's shown here, relative to your electrolyte. So once you have spaces where you're losing contact here, your ion transfer is, of course, significantly aggravated in these parts, and this is, of course, compromising your activity. And we have something like thermal expansion and strain. So also expansion, of course, in the short term might destroy your electrolyte. So by expanding your cathode, you can also micro crack the electrolyte, for example, and therefore leading to additional short circuit or leakage currents. So this should summarize for you that there are various aspects which you have to consider when developing cathodes due to this variety of degradation mechanisms. The fact that the cathode is subject to so many degradation mechanisms makes it very important to understand the effect of these degradation mechanisms. See, it is very simple to say we have a cathodic reduction and simply a reaction of oxygen to oxide ions, for example. But what's happening actually is a multi-step process which involves a complex interaction of interfaces. So I want to have a closer look with you now at what is actually happening at your cathode and what you require there to have a most optimal reaction. So as I already told you, the reaction at the cathode is a multi-step process, and this is necessary so you can conduct this reduction reaction. First of all, what you need to do is you need to adsorb oxygen to your cathode and dissociate it into a species which we will just call oxygen adsorbed, basically. In the next step, you have to reduce your material on the cathode, forming this oxide ion from your oxygen adsorbed species. So this would factually require 2 electrons to form this oxygen 2-, this oxide ion. And then the third step is to actually incorporate this oxide ion into the electrolyte vacancy and then transport it via this caterpillar mechanism to the other electrode and react it on our anode. So what we need for a reaction is basically 3 species. We need a gas phase oxygen, we need the cathode, which will provide us with electrons, and we need a contact with the electrolyte, which will provide us with vacancies to incorporate the oxide ion. And this is how you can imagine this kind of system. And we speak about a so-called triple phase boundary here, which allows us to perform this reaction of 1/2 oxygen, 2 electrons reacting to 1 oxide ion here. So what do we have here? We have a cathode particle here basically, which is providing us with electrons, as you can see here. We do have a gas phase, which is providing oxygen, and we do have an electrolyte, which is taking oxide ions away from the reaction. So basically, this reaction can mostly take place at certain spots on your material, and this is where the gas phase, the cathode material, and the electrolyte meet. And this is why we call it triple phase boundary, because each of these components here is provided by one phase. As you see, and as we saw before, the oxygen is provided by the gas phase here, the electrons are provided via your cathode material, and the oxide ions are then taken from here to the electrolyte. So what we aim for is actually a maximization of these triple phase boundary areas here, as more of them will allow us for more active sites and thus for higher reactivity. So if we want to improve our cathode properties as a whole, we want to have a spatial proximity of these 3 phases and a maximum amount of these kind of places where we can facilitate this reaction.